Okay, this is sort of a massive problem here. It's two parts, but let me show you what a glory hole looks like, what they call a glory hole. A glory hole is a pipe that comes up out, and then the top of it is flared like a funnel. Okay, so let me just show you here what it says. It says a glory hole is a vertical drain pipe that keeps the water behind a dam from getting too high. The top of the glory hole for a dam is 14 feet below the top of the dam and 375 feet above the bottom. The hole needs to be pumped out from time to time. Okay, so from the cross section in the figure, we see that the glory hole is a funnel-shaped drain, and the throat of the funnel is 20 feet wide, and the head is 120 feet across. So let me just make it a little smaller so you can see what I'm talking about here. So actually this throat is 20 feet wide, which means it has a 10-foot radius. And then this is the water level. So this is 325 feet above the bottom of the dam, it says. And then let's see what else we got. Make sure I've got this all written correctly. The outside boundary of the head cross section are actually quarter circles with 50 radii. So what we're saying here, this is just a quarter circle, and this is a quarter circle with radius 50. So that'll come into play later. And the glory hole is formed by rotating a cross section of that around the center. Consequently, all horizontal cross sections are circular discs throughout the entire glory hole. So in other words, they're saying that from here over to here is actually like a circular disc. Okay, and now it says calculate the work required to pump water from the throat of the hole and the funnel portion. Now actually, if you pump the water from the throat of the hole and pump the water from the funnel portion, then if you added those together, that would give you the total work required. So the first thing I'm going to do here is I'm going to think about pumping water from the throat. Okay, so remember, we're going to think of like a little slab here of water that's got to be pumped from the throat. So a typical slab in the throat here would be between the planes at y and y plus delta y. Okay, so the volume of this slab, in other words, the volume of this slab of water would actually be here pi r squared. Now, since we know the radius of this is 10, then it would be pi times 10 squared. And then the delta y is just the height of this slab that we're dealing with right here. So that would be the volume. So actually that sort of represents the volume of our slab. So delta V here is like the volume of our slab. Okay, now the force, F of y, required to lift this slab is equal to its weight, and we're going to use 62.4 pounds per cubic feet for water. So actually, if we want the force, it's actually its weight times its volume. So I guess I didn't finish that sentence, but it's the weight times the volume. So if you take this volume is 100 pi times delta y, and then if you multiply that by 62.4, you get 6,240 pi times delta y pounds. And now let's talk about the distance through which this must act to lift the slab to the top of the pole is actually 375 minus y feet. Okay, so the distance here is, as we move it y units, then the total distance from here up to here is 375. So if we've moved it, say we moved it this far, that's y units. So we would still have 375 minus y units to go. So anyway, that's what we're talking about there. Okay, now so the work would be that force times the distance, 375 minus y. Okay, and so that's where the 375 minus y comes from. Okay, so now we put that in our integral right here, and then we're going to integrate it from 0 to 325. And let me tell you why we're going to do 0 to 325. Okay, because 325 is actually where the throat of the pipe ends, and then it becomes this flared region, and we're going to do the flared region separately. So anyway, so that's why we're integrating from 0 to 325. Now this is just a simple linear function of y, so you can certainly perform this integral. So go ahead and integrate this from 0 to 325, and I got a rather large number there. It looks like it's in the billions. 1,353,869,354 foot-pounds to move that water. Well, all that water's heavy, and we had to move it a long distance, so that kind of makes sense there that it would be a large number. Now, to pump the water through the funnel, we actually are going to pump it from a height of 325 feet to a height of 375 feet. Okay, so now we need to get the volume. We need to figure a way to get the volume of the slabs in here. Okay, so let me show you how we're going to get that volume. So to find the volume, I actually need to know the radius of this circle, and so I'm looking for the radius, which would be from here over to here. Now what's going to be helpful in finding that for us is to actually give this circle here a formula. So this circle that would go all the way around there, we need a formula. So we know this is a quarter circle, so if you consider the center would be right here, and right here we could say, you know, x is 60, because that point is 60, 375, and then the y value is 325, because we can see here this point is the point 10, 325. So therefore we can say that the center of that circle, or that the formula for that circle, is x minus 60 squared plus y minus 325 squared equals 50 squared. Okay, because we know the radius of the circle, those circles, is 50. Now, if we solve this for x, we can just subtract. This part right here from both sides, and we get 2,500 minus this quantity squared. And then if you take the square root, which we'll just use the positive root, you'll get x minus 60 equals the square root of that. And so then to get this x value, which we need this x value right here, add 60 to both sides, and then you get x equals this square root plus 60. Okay, so that's the radius of my circular slab. So then the approximate volume of my slabs would actually be that value. You know, remember we do pi r squared, so we would have pi times the radius squared, and then we multiply that by the height of the slab. So the height of this circular slab we're going to just call delta y. Okay, so now let's talk about the force. So the force for each disc, we would take the weight of the water times the volume up here. So weight of the water times the volume would give me that. And then the work would be the force times the distance. So here's the force right here from the previous expression. And then the distance that we're going to move it is, again, this time it's 375 minus y again. So that's the distance that's going to be moved. Okay, so now we have our work expression. So now we can put that in this integral here. and then we integrate this function, and I didn't try to integrate it, but you integrate it from let's see, I'm not sure, is it 0 to 325? Okay, I thought that was wrong. So you actually integrate from 325 to 375, because you're actually only going from here up to here with this portion of the water. So 325 to 375. So anyway, don't worry about trying to calculate that integral. It's probably pretty nasty. But anyway, that's how you would set up the problem there. I'm not sure if this answer is correct, because I checked this integral in Wolfram Alpha and I got a different value. But anyway, this is how you set it up, though. But again, change the limits of the integral. Make sure that you go from 325 to 375 on the limits of the integral. And that pretty much ends this section. And the last section I'm going to do on these applications of integrals is a section on fluids. So I'll see you when we get to fluids.